there are different levels of problems on tests. There's certain problems which is just, did you remember it? Can you write it down on the test? The kind of regurgitation type problems. So a lot of those, and then there are other problems where, okay, maybe you see a pattern here, maybe you can apply it to something new. So the pattern was, okay, the pattern was these reactions are similar to acid-base. Can you do the same thing that you did for acid-base for redox? It's essentially the same steps. Did you notice the steps were the same, basically? A little bit more complicated, but essentially the same. And so that's a little bit more difficult, where you got to apply something that you've done acid-base to something new that you haven't necessarily done redox, but I gave you the pattern. Okay, and then you have another level of problem where it's something you hadn't seen before, but maybe something that you've seen in lecture or homework can help you solve that particular problem. And so we have a mix of those here. And so what you're going to do is you're going to work these out. I'm going to check them off as you go along. But let's go through the first one. Since I see, maybe with a little more time, if I gave you another 10 minutes or so, maybe some people would have it. All right, so let's go through the steps for redox, but I noticed that nobody got the answer. So, first thing we do is inventory. So, what is the inventory? This. Okay, Fe3 plus, Cl minus, Ag plus, NO3 minus, H2O. H2O liquid. Right. Water is always present in aqueous solutions. Okay, then we go down the list. And, yesterday I wrote down, people always look at the list and go, okay, the bottom right is this and the top left is that. Well, it's not always the case. Because if you look at the list in our classroom, it's inverted. Did you notice that? And so you don't use up or down. It's like if you're out in outer space, what's up, what's down? Is there an orientation? Well, it's the same thing with this chart. It could be like this, it could be like this, or it could be sideways. And so you don't use up or down, you use what to get your bearing? Not left or right. You use fluorine and lithium, and so that's it. Fluorine's the strongest OA oxidizer, and lithium is the strongest RA. All right, so iron 3, what is it? OA, RA? Iron 3 is an OA. Chloride. Chloride is there. Chloride is on the list. Chloride's an RA. Silver ions. OA. Nitrate. OA. Asterisk. Water. Water is an RA. Okay. It's both. It's both an RA and an OA. Water is kind of interesting. It can go either way. It can be a reducing agent, that is, give up electrons, or it can be an oxidizing agent, i.e., take electrons. And so it's, remember amphoteric for acid bases? It's similar. It's analogous here. It's both an oxidizer or reducer, but we don't have a fancy word for that. So we'll just call it both. Are there any other species that are both?
Fe2 plus.
Fe2 plus. Fe2 plus is both, right? Do you see it? It occurs on the left side and the right side. So Fe2 plus is like that amphoteric type species. Any others?
O2, yes.
O2? Where do you see O2?
Right here on the second line, on the left, and on the right, on here.
Okay. O2, yes. Do you see O2 occurs on both sides, except they're different.
It appears twice.
O2 on the left has what in combination? H plus, acid. On the left it has water. And so it's slightly different. It's not the same under the same conditions. Okay, so O2, yeah, somewhat. And
Tin2.
tin2. Tin2, SN2 plus appears on both sides. And chloride does not. Hydrogen peroxide does. Hydrogen, it doesn't mean it's equal, you know, because hydrogen peroxide is a much stronger oxidizer than it is a reducer. It just means it can go either way. You know, the same thing with water. It doesn't mean it's equally as good. In acid-base properties, it is equally as good. Any others?
Lead-2 plus.
Lead-2 plus, yeah, good. You found a lot, that's good. And so there are more. How do you recognize those species? How you recognize those species is you look at the chart once in a while and actually read it. A lot of people don't actually read this chart, and they end up missing. You know, they'll see, let's say they'll see iron 2 plus, so they see it on the left, but they don't bother finding it on the right because they never knew it could occur on both sides of the chart. And they end up, and so you want to be aware of that. And so take a look at the chart once in a while. And then there's something else you want to be aware of, and that is, for example, nitrate. Nitrate doesn't occur alone. What does nitrate occur with? H plus. It's actually nitrate plus 4 H pluses. So we need H plus. We need acid in there. Well, when I look at the inventory, is there any H plus in my inventory? No. And one of the things is, you know, even though it says 4 H plus, does that mean it needs 4 molar H plus? No. What it means is it reacts in a 1-to-4 ratio, no matter what the concentration is. And so what we need for these to work out, and the same thing for metathesis, what we need are concentrations that are fairly high. And so our assumption, our base assumption with this is that we're dealing with 1 molar concentrations, both for the metathesis, the acid base, and the redox. And so you might have learned in Chem 4 that there is a tiny bit of H plus in water, which causes it to be pH 7. Have you heard that? But you know, that concentration is so small, it's not enough for this particular reaction. We needed a 1 molar for it to operate as it does here. And so what that does is it changes nitrate's ranking. This is something you can do in Chem 1B. You can do it quantitatively. You know, how does the strength of nitrate as an oxidizer change with H plus? I mean, why should it change with H plus? Because you know, it looks like H plus has no impact. H plus stays +1 on the left, and H plus stays +1 on the right. So it doesn't change oxidation state. If H plus is neither gaining nor losing electrons, then how is H plus participating in this particular reaction? Why do we need H plus?
Doesn't it increase the strength of the nitrate?
It's going to increase the strength of the nitrate, but how? Why do we need H plus? What is the pattern? What's the pattern? Why do you see a pattern with the H pluses? You guys remember the pattern? This would be an example of a regurgitation problem on a test. A regurgitation problem is what is the pattern with the H plus in the redox chart? That is, it's just a memory type problem. Do you remember what we said about it? Or maybe you could see it. It doesn't have to be a memory problem. You could just look at the chart and figure it out yourself. But we had already talked, didn't we talk about it? Or
They're always used to make water.
Hmm? Yeah.
They're always used to make water.
Yes, right. That's the pattern. The pattern is if we don't have the H plus, right, we aren't going to form water. If we don't form water, what would we form as an alternative to water? Not hydroxide. If we formed hydroxide, it'd probably still be okay then. But we don't even have an H plus to form hydroxide. We would form oxide. Is oxide stable? No, oxide's highly unstable. And so this is why we need the H plus. We need the H plus to make the stable product water. Otherwise it's going to be highly unstable oxide, which means that the driving force isn't going to be so big. And so for something like nitrate, the way I like to think about it is one, there, you know, the H plus is forming water, which is going to be a stable product, versus oxide, which is a highly unstable product. Or the alternative way of thinking about this is this. Let's say you're trying to bake a cake. If you're trying to bake a cake and you have flour, but you ran out of sugar. So if you have flour, you ran out of sugar, are you going to go ahead and bake your cake? Are you going to get a cake? No, I mean, it's going to taste awful, right? It's not really going to be a cake. The same thing here. We could have nitrate, but if there's no acid, are we going to make the product? Are we going to make water? Nitrate with no acid doesn't make water, does it? And so it's the same thing here. Since we're missing the H plus, when I talk about H plus, I'm talking about a significant concentration of H plus. We need a significant concentration, not just the minuscule amount naturally present in water. Since that's the case, we eliminate this. You know, what it's going to do is it's going to weaken nitrate significantly. Don't get me wrong, all nitrates are dangerous. You know, chemists are always worried about nitrates. You know, but for our purposes, you know, we don't have the Chem 1B tools yet to calculate how much it's weakened depending on the H plus concentration. So we'll just kind of ignore it here. And so there's no H plus, therefore this is going to be quite a bit weaker as far as redox properties go. All right, so now we have three oxidizing agents that we're going to consider. Which of these three will be the strongest? Silver ion, Ag plus. Okay, so we have the strongest oxidizer here. The strongest oxidizer, the half reaction is going to be this. Ag plus plus 1 electron yields Ag solid. Now, what's the strongest reducing agent present? The strongest reducing agent is, I heard chlorine, but chlorine's wrong. That's not chlorine. You know what chlorine is? Cl2. This is called chloride. Chlorine and chloride, are they the same thing? No, not even close to being the same thing. You know, chlorine is very reactive, very dangerous. Chloride is pretty unreactive, pretty stable stuff. And so what's the strongest reducing agent? H2O. Does everybody see that? H2O. So based on the chart, H2O is the strongest. But, you know, there's a bit of memorization in chemistry. And so this is based on the chart. H2O is the strongest. However, you have to memorize one exception. And this is it. Just one. The one exception that you have to memorize is this. It has to do with kinetics versus thermodynamics. Have you ever heard of kinetics? Like the speed of the reaction? And what we have here is this. If we compare chloride, if an oxidizer comes along, what does the oxidizer want to do? The oxidizer wants to take an electron. So how hard is it to take an electron off chloride? Well, the oxidizer comes and plucks the electron off the outermost, what do you call it? The outermost shell, right? And so the oxidizer comes, pulls the electron off, and we get chlorine. However, for water, water is a bit more tricky because, you know, for water, what we're going to get, the oxidizer comes along, and does the oxidizer just pluck off the electrons off the oxygen here? Maybe pluck one or two of those? No. No, what has to happen in water when an oxidizer comes along is everything has to get rearranged. And so we end up with O2 gas, 4H plus, and electrons. And the oxidizer plucks those off, but do you see how the bonds are broken? The electrons are totally rearranged, right? And so what we have here is a situation of short-term versus long-term payoff. You know, what would you rather do? This is the analogy I'll try to use. I used a different analogy this morning, but would you rather do let's say the payout is not that different, you know, between chloride and water, the payout meaning this, how much work you have to do. You get less pay for this, but it's a much easier job. You make nearly the same amount of pay for this, but it's a much harder job. Which one do you want? Yeah, if you're going to make about the same amount of pay, then wouldn't you want to do the easier job versus the harder job, right? Well, that's the situation here. You know, in nature, yes, you're going to get a little bit more energy payout here because this is a little bit more stable than this, but not hugely so. But comparing the amount of work that you have to put in, this is so much easier to accomplish that the nature is going to take this path. It's going to be the path of least resistance here. You know, over the long term, it eventually could settle to this, but initially it's for sure going to go this way, the easiest path, right? And so it turns out that even though water, based on the chart, is the strongest, and these charts are based on energies, thermodynamic energies, not kinetic, it turns out that chloride is easier to oxidize, what we call, and so chloride will be a better reducing agent. And so you remember that here. Chloride will be a better reducing agent. RA, because kinetics. Kinetics is talked about in Chem 1B. So if you don't know kinetics, don't worry about it. All right, so here we have to remember the exception, so we're going to cross that one out, and then we're going to circle this one instead, right, because of this. So let me erase this here. So what this means is that if chloride's giving up the electrons, then we just copy the equation off the chart. 2 chlorides goes to chlorine plus 2 electrons, like that. And then we add up the 2 half reactions. We add them up, making sure that the electrons cancel. I mean, we have 2 electrons here. We only have 1 electron here. Therefore, we're going to multiply this one by 2 all the way across to get 2 electrons. And so that these 2 electrons here cancel these 2 electrons here on the left and the right. And so the overall reaction is going to be 2 Ag plus 2 Cl minus yields 2 Ag solids plus Cl2 gas. So then we look for driving force. So what is the driving force for this particular reaction? Yeah, we got a precipitate of silver metal and a gas form. We got 2 driving forces, which is good. It's better, right? Would you agree? Precipitation and gas formation, driving force. Yes? Precipitation and gas formation, driving force. How many people agree with this? 1, 2, 3, 4, 5. How many people disagree with this? 0. The rest don't know. No. That's wrong. That's wrong because why? That's wrong because this is a redox. Those driving forces are for metathesis. But then you might argue, why can't we use these driving forces for redox? Why don't these driving forces work for redox? Why? So what would you tell your friend if they asked you, why don't those driving forces work for redox?
First, it doesn't necessarily mean that the oxidation numbers change.
Yeah, all right. That's kind of on the way there. These driving forces do not work for redox. They work for metathesis in acid-base. They work for metathesis in acid-base because if you have a sodium ion in metathesis on the left, on the right you're going to have a sodium ion. Now, sodium ion versus a sodium ion, are they going to be roughly the same? Yeah, they're going to be the same, right? The only difference is who they're partnered with. That's it. That's metathesis. But in redox, you would have not sodium ion on the left and sodium on the right. In redox, you'd have sodium metal on the left and sodium ion on the right. Right? And so you might go, you know, I don't want to destroy my precipitate of sodium metal to form sodium ion, right? That would be an anti-driving force. But did I show you the video of sodium metal? What happened when they put sodium metal into that lake? Yeah, huge amounts of energy. And so what it tells you is redox is different. Redox is different because the oxidation states change. When the oxidation states change, it no longer is the same. You can't call it sodium and sodium. It's sodium ion versus sodium metal. You can't call it chlorine and chlorine. It's chloride versus chlorine. You know, if you're going to inhale chlorine, it better be chloride. You don't want to inhale chlorine gas, do you? No. And so the stability is dramatically different. The classic example is this: water. H2O liquid. 2 H2O liquids goes to 2 hydrogen gas plus oxygen gas. Oh, I'm forming 3 moles of gas. That must be a huge driving force, is it? No. Why not? I'm getting plenty of gas. I'm going from this little bit of liquid. This is only 36 milliliters of liquid, and to about 75 liters of gas. You know, going from 36 milliliters of liquid to 75 liters of gas, that's huge, right? Gas formation. Yes? No, this is not a driving force because it's a redox. Right. There's no way this is going to happen. Does your water decompose into hydrogen gas and oxygen gas? No. There's no way that happens. So anyway, what is the driving force for redox? What did we want to go from stronger to weaker oxidizing agent, and stronger reducing agent to weaker reducing agent. And so over here, silver ions, that's our oxidizing agent. Chloride is our reducing agent. Now we have to go backwards. When we go backwards, it's easy to look up here at the half reactions. Silver going backwards loses electrons, so that's our reducing agent. And then chlorine going backwards takes electrons. And so this will be our oxidizing agent. And then we compare the two strengths. Silver ion versus chlorine, which is a better oxidizing agent? So look at the chart. Chlorine is a better one. And that means silver must be weaker. And that means the reducing agents have to follow the same pattern. So is silver metal a better reducing agent than chloride ion? Yes?
Yes.
That means chloride is more stable than silver metal, right? And so looking at this, do we have driving force? No. And so the correct answer was there's no driving force. Therefore, no reaction. And so it turns out that the only reaction that we're going to see for that, number one, is metathesis. Okay, there was no acid base, there was no redox. All right, for the remainder, I want you to do redox first. You know, take a look. What are the potential redox reactions you're doing? And then bring them up, and I'll check them off. The only one that might not involve redox is number 8 here. You know, there's a second step involving further reaction. So a secondary reaction. This doesn't have to be redox. It could be metathesis or it could be acid base. All right, so go ahead and start working on those and then bring them up to get them checked off. So that's what we're doing today.